Hello, my name is Nathaniel Masintabon, and today I will be covering chemical reactions, which is the process of converting substances into different substances. Now, there are two different types of reactions, chemical and combustion. Combustion, which creates heat and also has oxygen within its reaction. Now, equations of chemical reactions consist of reactants and products. And similar to a math formula, have to be balanced numerically. Now, there are four states of reactants, which they can be in gas, liquid, solid, or aqueous, which is mixed with water. And for example, this methane reaction, this methane combustion, you can see that the molecules are not balanced. There's one carbon atom, four hydrogen, two oxygen. Here, there's three oxygen, only two hydrogen. So what you need to do is multiply the various sides with coefficients since you can't change the structure of an atom. So using this, you're able to balance out the equation.
Hi everyone, my name is Valerie Hilsa. I'm going to talk about what I learned from chapter 4, and my topic is limiting reactant, theoretical yield, and percentage yield. So when you have two reactants in a chemical reaction, they usually do not run out at the same time. Whichever run out at the same time, it's called limiting reactant, which determines the maximum amount of product that you can make out of it, which is called the theoretical yield. So we had an example from class that is also mentioned on the slices, which is the great pizza analogy. So if you have enough crust for 4 pizzas, cheese for 5, but only enough tomato sauce for 3, you can only make 3 pizzas. So you see, in that case, the tomato sauce is the limiting reactant. And got it. So I also learned that in real lab conditions, you rarely can get the full theoretical yield because of spills, incomplete reactants, or some other losses. So in that case, we use this equation for the percentage yield. The actual yield divided by the theoretical yield times 100% to measure how efficient the reaction was.
Hello everyone, I'm Sonic Oyalo, and today we got quantities in a chemical reaction. Let's go. So, to start, we got the amount of every substance is gonna be related to the amount of each substance in a reaction, in a chemical reaction. Almost the same explanation, but that's what we learned. So, we got three things. We got the law of conservation of atoms. I mean, conservation of mass. Then we got the balancing of chemical reaction by balancing atoms. And then we got the most important one, uh, the numeration of quantities. If I don't remember bad, it's the study of numeration of quantities. This one is gonna be called um, stoichiometry. For this one, stoichiometry, we got some examples. The coefficient in a chemical reaction specify the relativity amounts in moles of each of the systems involved in the reaction. We got some examples here, but I cannot explain it that well. So we will need to go to the making pizza example. The making pizza example is simple. The amount of pizza that we're gonna make is gonna be dependent on how much ingredients we will have. Okay, so we need to have the specific amount of ingredients if we got more than one pizza. Example, we got one crust, 5 ounces of tomato, uh, 2 cups of cheese, and then we can get one pizza. But this can be explained mathematically. This is another example. We got the relation. They can be expressed mathematically. 1 crust, 5 ounces of salsa, 2 cups cheese, 1 pizza. We can compare the amount of pizza that can be made from 6 cups of cheese. 2 cups of cheese, 1 pizza. That means 6 cups of cheese per 1 pizza over 2 cups of cheese is gonna be equal to 3 pizzas. So that is gonna be the explanation of this specific one. If we see it like this, it's gonna be more easier, so we can understand how we can combine them and make one reaction, one final reaction, and make it work. Thank you so much. Let's go with my partners.
Hi, Dr. Sharma. This is my video. Whoops, I meant chapter 4. One of the things that I struggled with in this chapter was just making sure that I had my fractions, like my conversions placed in the right area. So when it came to like changing things from mole to grams and back and forth, and the best way that I tackled that was just writing it all out like fully, and like sometimes I like shorthand it, and that's where I get confused. So I was like, okay, the best way for me to make sure that I'm canceling things out is to just write it out fully, like, and just not worry about if it's slowing me down or whatever. Just write it out fully. So that's what I did. My topic for chapter 3 is I did a reactants, limiting and excess reactants. So I did my little board here. Limiting reactants, the reactant that is completely consumed and determines the amount of the product formed. And then excess reactant is the reactant present in a greater amount than necessary to react with all the limiting reactants. So the limiting reactant is basically when you're going to make something, it's the ingredient that you have least of. So it's the one that you're going to run out first. Whereas excess, I think I read in the chapter that excess is often like put out excessly just to make sure that you run through the whole limiting reactant. Sometimes it's like just to make sure that you run through everything of whatever the limiting reactant is, you'll put excess of another reactant just to like have it abundantly. So for example, I put example, suppose we have 5 moles of CO and 8 moles of H2 for the chemical equation below. So it's carbon dioxide plus 2 hydrogen 2 equals, I didn't write that down, but it's CH3 hydroxide. So in this case, we want to figure out what is our limiting reactant and what is our excess reactant. So the best way to do that is to figure out how much of each would we need to run through of each. So in this side, we have 8 moles of H2. This is where I wrote it all out, just to make sure I got the right things canceling. In this case, for every mole of CO, we have 2 moles of H2. So that's what I put here. So 1 mole CH, and then basically these cancel out. So you'll have 8 divided by 2 equals 4. Ta-da. And what this is saying is we would need 4 moles of CO to consume all of the 8 moles of H2, which we currently have 5 moles. So that already is kind of giving way, but let's go ahead and look at what our other one is. We have 5 moles of CO. In this case, we want to figure out how much of CO we would need to how much H2 we would need to consume all of the CO. So in this case, to convert, we would, for every 2 moles of H2, we have 1 mole of
CO, so it would be 5 times 2, giving me a need for 10 moles of H2 to consume all of that, which we do not have. We actually only have 8 moles of H2, making H2 my limiting reactant and CO my excess reactant. And whoops, I think I said that was chapter 3. It's actually chapter 4.
So one thing I learned about in chapter 4 was the difference between theoretical yield, percent yield, and actual yield. So theoretical yield, that's basically the maximum amount of product that can be produced in a chemical reaction, and that's based on the limiting reactant. Actual yield, that would be the actual amount of product produced in that chemical reaction. And the percent yield compares the two, theoretical yield and actual yield, and that tells you how efficient the reaction was. I don't think this topic in the chapter was too difficult to remember. It was a little tricky at first because, all 3 of them do sound the same. But, I just remembered how theoretical yield, that's the amount of product that you expect to get. The percent yield, that compares the theoretical yield and the actual yield. And then the actual yield, that's the amount of product that you actually do get. So it was pretty easy after I remembered that and I did a few practice problems.